This music of the planets is not just someone's fantasy. It is an animation of the real planetary system TOI 178, in which 6 planets are known. The motion of 5 of them is astonishingly synchronized in an orbital resonance. The rhythm of the sounds produced by the planets here is not random. A planet makes a sound either when it completes a full orbit, half an orbit, or when 2 or more planets align in a straight line. Yes, the notes were chosen deliberately for clarity and effect, but even if all planets produced the same note, the repeating, orderly rhythmic pattern would still remain. The planets sing only in this animation. However, their synchronized orbital dance is happening in reality, and this can be demonstrated not only through sound, but also through visual techniques. Here are the orbits of our home planet Earth and Venus, and if you draw a line through the points of their closest approach, the planets trace out a pentagram. What would that mean? And if, as both planets move along their orbits, you continuously draw a line from one planet to the other, you eventually get this intricate pattern. What does it all mean? And is there some hidden significance in it? Hidden or not, there is some meaning to it. People have been searching for patterns and order in the universe for millennia, and in these searches we do not always arrive at the correct conclusions. It's not hard to imagine someone seeing what I just showed you and deciding that everything here looks far too orderly, that it clearly couldn't have come together on its own. Perhaps they might think the planets were arranged in these configurations by someone. But whatever the true case may be, it does look genuinely fascinating, and it would be worth trying to figure out how it all turned out this way. Today we're going to talk about orbital resonances, what types there are, how common they are in the universe, look at several fascinating examples, and most importantly try to understand how planets synchronize in such an astonishing way. What creates orbital resonances, and what in turn do they themselves lead to? I'm Andrei, and this is Cosmos Elementary. Interestingly, people were already exploring the idea of music of the planets 2,500 years ago. Well, not people, but one particular person, Pythagoras. Well, at least according to the stories. We don't have much reliable information here, so according to the legends, he was the first to discover that musical notes can be described mathematically. But he didn't stop at strings of different lengths and properties. He applied similar principles to the cosmos. The logic was this. On Earth, objects in motion produce sounds. The planets are in constant motion, at least as it was believed at the time, orbiting a stationary Earth at the center. Since they move, each planet can produce its own unique sound, its own note, though humans cannot actually hear it. This idea of planetary music is called the harmony of the spheres. Something similar was considered much later by the famous astronomer Johannes Kepler, the author of Kepler's laws, which later formed the basis for Newton's law of universal gravitation. In his work, The Harmony of the World, Kepler also tried to find a connection between the motion of the planets and musical harmonies. Here we can already see some similarities with the idea of orbital resonance. With the emergence of the law of universal gravitation, the question of the stability of planetary systems became more pressing, and one of the first real orbital resonances was discovered by Laplace. This is the resonance of Jupiter's 3 Galilean moons, Io, Europa, and Ganymede. Of course, today we have a completely different understanding of all this. We know many examples of resonances in space, systems synchronized in specific ways, and at the same time we see that this does not happen everywhere. So this is a dictionary definition of a resonance, and I quote, "A vibration of large amplitude in a mechanical or electrical system caused by a relatively small periodic stimulus of the same or nearly the same period as the natural vibration period of the system." There's actually quite a strong connection with sound here, so the associations we talked about earlier aren't surprising. Most likely, the majority of those who know something about orbital resonances, when they hear this term, immediately think of those I showed at the very beginning. But in reality, there are several types, 3 main ones. The most well-known resonance is called mean motion orbital resonance. The nature and underlying cause of the phenomenon are quite subtle, and we'll talk about that today. And the essence of the observed effect is fairly simple. The definition usually goes something like this. An orbital resonance is a phenomenon in which the orbital periods of two or more bodies orbiting a larger body are related by small whole numbers. Resonances are denoted as 2 to 1, 3 to 2, 4 to 2 to 1, and so on. One of the simplest examples is 2 to 1 resonance. This means that two bodies orbiting a third body, for example, two planets orbiting a star or two moons orbiting a planet, are positioned at such distances from the central body that the second, more distant object takes exactly twice as long to complete one orbit as the first. So let's build a system with this kind of resonance ourselves in Universe Sandbox. Let's take the Sun and place Earth at the distance it actually orbits the Sun on average, that is at 1 astronomical unit. For greater accuracy, we'll manually adjust the orbital period or year so that it lasts 365 days. Now let's add another Earth and give it an orbital period exactly twice as long, 730 days. For clarity, we'll enlarge the planets so they're visible. And then run the modal. Besides the obvious fact that the outer planet takes exactly twice as long to complete an orbit as the inner one, which we've set ourselves, it's also interesting that the planets always meet at the same points along their orbits. And this is an important point that we'll discuss in more detail later. Here I've made another example of a 4 to 3 resonance. This hypothetical cycle starts at a certain point. During the cycle, the outer planet completes 3 orbits while the inner one completes 4. And in the end, they return to the same point where the cycle began. In a 5 to 1 resonance, the planets meet several times during the cycle, but in the end, they also return to their starting point. It is not surprising that it seems like a resonance system was made on purpose. In our model, we had to adjust the orbital periods so that the planets always met at the same point. Without a resonance, we could have placed the planets almost anywhere at random, but in reality, it's a lot trickier than that. In the system I showed at the beginning, TOI 178, there is an entire chain of resonances. Out of the 6 planets, 5 are in a 2 to 4 to 6 to 9 to 12 resonance. That is, in the same amount of time that one planet completes 2 orbits, the next completes 4, the one after 6, and so on. Here we're starting from the other side. But before we talk about how this actually happens and how planets synchronize their motion, let's take a look at what other types of resonances exist. Some of you are familiar with another type of resonance, which is called spin-orbit resonance. And from the name alone, you can probably guess what it's about. Spin refers to rotation around an axis, and orbit, well, of course, refers to motion along an orbit. So this is about the synchronization of these two types of motion. We've discussed this in the context of tidal locking or synchronous rotation. And the closest example is, of course, our own moon, which completes one rotation on its axis in the same time it takes to orbit Earth, which is why we always see only one side of the moon. In other words, the moon is in a 1-to-1 spin-orbit resonance. What this has in common with the orbital resonances I mentioned earlier is that there is a mechanism by which an object, initially not in such a resonance, becomes locked in a 1-to-1 resonance due to tidal interactions. And this is a natural outcome of orbital evolution for many bodies. In fact, almost all of the major moons of planets in the solar system are in 1-to-1 orbital resonance. In other words, they're tidally locked. As are some exoplanets that orbit very close to their stars. But just like with regular orbital resonances, they can come in different forms. It's not limited to a simple 1-to-1 resonance. A good example in the solar system is Mercury. It rotates slowly on its axis, but it's not tidally locked. Instead, it is in a 3-to-2 spin-orbit resonance. It completes one orbit around the Sun in about 88 days, while it rotates once on its axis in about 59 days, which gives us the ratio of 3-to-2. Another type of resonance is called secular resonance. I know it's not what you might be thinking. This basically means long-term, and that name isn't accidental. The cycles of these resonances unfold over much longer timescales, thousands or even millions of years. And here, it's not so much that bodies themselves are involved, but rather their orbits, the orbital parameters and their precession. As we know, perfectly circular orbits do not exist. All of them are elongated to one degree or another. For clarity, let's take an orbit with a high degree of ellipticity. Such an orbit has a point closest to the central body, the pericenter, and the farthest point, the apocenter. You can also draw a line between the pericenter and the apocenter called the apse line. The key point is that the orbit and the line are not always oriented in the same direction. Not only does the body move along its orbit, but the orbit itself gradually shifts in this way, a phenomenon known as precession. And this kind of orbital precession of two or more bodies can also become synchronized in a certain way. In the simple case when there is no resonance, the pericenter of the two bodies' orbits point in different directions. But when a resonance is present, their precession occurs synchronously. I've only found one animation that clearly shows this, and I'll leave a link to it in the description. Such synchronization can also involve other parameters, such as the orbital inclination and others. But let's get back to the more familiar orbital resonances. This is a sonification, that is a conversion of some data into sound of another system with a long chain of resonances, the longest known to date. If in 20Y 5 out of 6 planets were in resonance, here all 7 known planets are. The longer such a chain, the less likely it seems that it's just a coincidence. A one-to-one spin-orbit resonance or tidal locking also often confuses people. They wonder how it could just happen that the rotation period equals the orbital period. It seems like something fishy is going on. But just as there is a mechanism that explains this quote-unquote coincidence, there are also mechanisms for ordinary orbital resonances. First, we can look at this question in a simple way. In systems with a resonance, the orbital periods align in a specific way. For example, in a 2-to-1 resonance, one planet might have an orbital period of 100 days, while the other has 200 days. What determines this duration? Why 100 days and not 110 days? It's actually quite simple. It basically comes down to the distance from the central body. Just as we need to accelerate a rocket to a certain speed so that it doesn't fall back to Earth, but instead enters orbit and stays there, planets also need a certain orbital velocity to avoid falling into the Sun. Moreover, the closer a body is to the star, the stronger the star's gravitational pull, the higher the orbital velocity must be. And this velocity depends not on the mass of the smaller body, but on the distance from the star. We can run a small experiment in Universe Sandbox. Yes, it's by no means the most precise tool, but it demonstrates the basic principles of classical mechanics quite well. Let's take Earth and place it again at a distance of 1 astronomical unit. That is the actual average distance from the Sun. Just by placing the planet at this distance, we see that its orbital period is 1 year and its orbital speed is 29.7 kilometers per second, just like in reality. Now let's remove Earth and instead put a pigeon. Now, better yet, a watermelon at the same distance from the Sun. And what do we see? The same orbital speed and the same orbital period. There might be a small margin of error, placing them in exactly the same spot down to the millimeter is tricky. And the watermelon, just like that, with the correct speed for that distance, casually orbits the Sun without falling into it. And once again, I'll remind you that we're still looking at this naively. One might think that for planets to end up in a 2-to-1 resonance, they just need to form at the right distances. For example, at a distance where the orbital period is 100 days and the other 200 days. And considering that in our galaxy alone there are hundreds of billions of stars and therefore planetary systems, from time to time we might find systems where planets happen to form at distances that put their orbital periods in resonance. However, in that case, orbital resonances would be rare. And if we look at how common this phenomenon is across the galaxy, we'll see that it is indeed quite rare. In roughly 5% of the discovered planetary systems, resonances are observed. And even more rarely do we see resonances involving more than 2 planets. The caveat here is that we might not have discovered all of the planets in all those planetary systems, so there might be more orbital resonances. So, is that our answer? It's just a coincidence? In a vast universe, even very rare events can happen, and that's all there is to it. But no, not quite. In general, scientists do consider the idea that in some cases, resonances in a system are present from the very formation, or almost from the very formation. But clearly, this cannot explain all cases. You might have already noticed a flaw in that logic, especially if we take into account what we know about the evolution of planetary systems. And what we know is that planets generally don't form at fixed distances from their stars and stay there forever. They tend to migrate, especially in the early stages of a system's existence when things are much more chaotic. Planetary systems are dynamic and complex. They contain many bodies of different masses. Not only does the star influence the planets and smaller bodies with its gravity, but all the bodies also affect each other. So, on one hand, yes, in principle, planets could form at distances from the star that put them in resonance. But then they would also need to stay at those distances. And again, planets move. After wandering through the system, they could settle at distances that put them into resonance. This is also possible, and there are mechanisms that can help make it happen. Most often, when a brief explanation of the phenomenon is given, it goes something like this. First of all, gravity is to blame. The idea is that as planets periodically encounter each other, they give each other a gravitational nudge, speeding up or slowing down one another. The analogy often used here is that of a swing. When one person is swinging and another pushes them, depending on how the pushes are timed, you can get very different outcomes. If you push out of sync at random moments, a person on a swing will just flop around. But if the pushes are timed synchronously at precisely the right moments, you can increase the swing's amplitude. Planets in resonance can do something roughly similar. And depending on the situation, this can lead to different outcomes. The system can become more stable and remain in resonance. There are self-correcting mechanisms where a planet drifting out of a resonance is nudged back into it. Or on the contrary, a resonance can eventually lead to destabilization, causing one of the bodies to leave the resonance and never return. This usually happens when one of the bodies is much smaller, for example, a planet and an asteroid in resonance. But all of this still doesn't really explain how bodies can end up in a resonance if they weren't in one before, or how they can stay in it once they get there. So if two planets happen to form at just the right distances to be in a nice resonance, and if we follow the logic that during their repeated encounters the planets gravitationally push each other, then eventually they should drift apart and fall out of resonance. And that's without even considering other mechanisms that can cause planets to move around the system. This also happens, and resonances can be far from being eternal, and many are unstable over the long term. We know that moons and planets move through their systems. Yes, if there were some perfectly symmetrical two-body system with a perfectly circular orbit, perfectly symmetrical bodies, no other objects around, and so on, then in theory such a planet could remain at the same distance from its star indefinitely. But in practice, of course, this is not the case. Planets and moons move through their systems not only shortly after formation, interacting with material in the still present protoplanetary disk and with other bodies, but also billions of years later. The most well-known example is our moon, which, due to tidal interactions between Earth and the moon, is moving away from Earth by about 4 centimeters per year, just like many other moons in the solar system. If, on the other hand, a moon is too close, it can gradually spiral inward and eventually fall onto the planet, like Mars' moon Phobos, which is slowly approaching the red planet. In the early stages, planets migrate constantly. It's believed that hot Jupiters, for instance, most likely originally formed farther from their stars and then moved closer. And in our system, at its dawn, there were more bodies, they influenced each other gravitationally, swapped places, and so on. Back then, a whole Mars-sized planet collided with the young Earth, leading to the formation of the Moon. There are actually a lot of nuances involved here. For example, the Earth is gradually moving away from the Sun, by a few centimeters each year. And why? Because the Sun is losing mass. As a result of nuclear fusion reactions, the Sun produces energy and loses it through radiation. Energy and mass are equivalent. In addition, the Sun loses mass through the solar wind. The less massive the Sun, the weaker its gravitational pull and the influence on Earth. As a result, Earth is slowly moving away. In short, planets, like moons and other bodies, don't stay in one place. They not only move along their orbits, but the orbits themselves change over time. So it's easy to imagine a situation where, say, two planets slowly moving through their system eventually end up on orbits that place them in a resonance. And here we face the same question as with lucky formation. If they were already moving, they would likely continue to move, so why should they stay on these orbits? And by the way, a good example of possibly broken resonances might be our own solar system. Yes, we do have quite a few examples of resonances like the already mentioned resonance of Jupiter's moons. Another striking example is the 3-to-1 resonance between Neptune and Pluto. This, by the way, is a beneficial resonance. Pluto's and Neptune's orbit cross, which means that in theory they could collide, but because they are in resonance, they never actually meet. Otherwise, it wouldn't have been enough that Pluto was downgraded to a dwarf planet. It could have also smashed into Neptune, and that would have been a real disaster, not a reputational one. But for some reason, among the main planets of the solar system, resonances aren't observed. At least, they rarely come up as examples when people talk about resonances. But in reality, some planets, even if not in exact resonance, are close enough to it. Strictly speaking, what we call resonance isn't synchronized down to the second. Here, though, the deviations are just a bit larger. Jupiter's orbital period is 4,332 days, and Saturn's is 10,759 days. 4,332 times 5 equals 21,660, and 10,759 times 2 equals 21,518, which is actually very close, but there is still a small difference of 142 days. At the beginning, I showed an animation of Venus and Earth. They also have a resonance close to 13-to-8. Earth and Mars are close to a 2-to-1 resonance, although the difference is a bit larger. In this case, the situation could be that in the past, the resonance between Jupiter and Saturn was even closer, but over time it became desynchronized. But in other planetary systems, we do observe even more precise resonances. And here, either we're just lucky to observe them at the moment before they've broken apart, which is in a way also true because resonances aren't eternal anyway. Still, they can remain stable for a very long time, for billions of years. This means that something must lock them in that configuration at least for a while. That's the special feature of resonant orbits. This is the asteroid belt of our solar system, located between the orbits of Mars and Jupiter. It's not a narrow strip, its width is about 1 astronomical unit, or over 150 million kilometers, or about 93 million miles. So, in other words, some asteroids are located closer to the Sun, while others are much farther away. They have different orbital periods, and their distribution isn't very even. But as usual, such illustrations can't capture all the details, so it's not very noticeable. If we plot a graph with distance from the Sun on one axis and the number of asteroids on the other, we will get this. And we can see that here, at a distance of 2.5 astronomical units from the Sun, or here, there are almost no asteroids. These gaps are called Kirkwood gaps. But why are these regions empty or nearly empty? And up until now in this image, I haven't shown you one important detail. Here it is. These gaps aren't random. They're located at distances from the Sun where asteroids fall into resonance with Jupiter. Here we see 3-to-1, 5-to-2, 7-to-3, and 2-to-1 resonances. The asteroids that used to be there received regular gravitational nudges from Jupiter. Jupiter is incomparably more massive than the asteroids, and over time, these nudges push them out of these regions. As a result, the areas clear out, and we see these gaps. This is a very clear example of the effects caused by orbital resonances when one body is much more massive than the other. But you might be wondering, in this case, what's the actual difference? Does a resonance exist here or not? If we have two bodies orbiting a third, they will inevitably meet periodically at their closest points. At these closest points, Jupiter's gravitational influence on an asteroid is maximal. So what's the difference? Does this happen in the same place every time or always in different places? And here, the important point is that the orbits, again, are not perfectly circular but elongated. Interestingly, there are very few detailed yet accessible explanations online of how this actually works. I found one article and a couple of the explanations I'm using are based on it. Another article and a great video by Steve Mould. Of course, I leave the links in the description. So, if both orbits are circular and two bodies meet at certain closest points, it doesn't really matter where exactly this happens. Here, here, or here. In theory, the distance and effects should be the same. But in reality, that's naturally not the case. In this article, for clarity, a special case is considered. The orbit of the body closer to the central object has a small eccentricity and is fairly close to circular, and the more distant body is on a noticeably elongated orbit. Also, for convenience, the inner body is made much more massive than the outer one, so that we can neglect the gravitational influence of the outer body on the inner one and instead focus on how the inner body affects the outer one. If we assume that bodies are in a simple 2-to-1 resonance, they will always meet at the same point. A situation where their meeting point coincides with the apse line running from the pericenter to the apocenter, and they meet on the apocenter side, will be stable. Why is that? Let's figure it out. In these images from the articles, a slightly different situation is shown. It does not coincide with the apse line. Here it is shown with a long dashed line, and here two situations are shown at once. Two planets shortly before meeting at their points of closest approach, and the planets after this encounter. There are also some arrows shown here. The arrows show the directions of individual components of the gravitational force. The length of the arrows isn't random either. If the point of closest approach doesn't coincide with the apse line, how does the larger planet affect the smaller one? Before the rendezvous, when the more massive planet is slightly behind the outer one, it not only pulls it toward the inner orbit, but also effectively drags the outer planet backward. After the rendezvous, on the other hand, it kind of pulls the planet along with it. If the encounter happened exactly on the apse line, these two effects, the backward pull against the orbital motion and the forward pull along it, would be equal because the two halves of the orbit would be symmetric. Here I've indicated this with dark blue arrows of equal length. But in this case, when the encounter happens elsewhere, it's not the same. That means that before the encounter, the inner planet pulls on the outer one slightly more than after the encounter. For clarity, the dark arrow on top is longer here. Effectively, the inner planet gradually slows down the outer one. And today we already talked about the fact that in order to stay in a certain orbit and not fall onto the central body, you need to maintain a specific velocity. Even a very thin atmosphere at the altitude of the International Space Station's orbit is enough to slowly but surely slow the station down. Without periodic engine burns, the station would eventually fall to Earth. The outer planet, however, doesn't have the luxury of engines. So, due to this braking, its orbit gradually shrinks. And as the orbit changes, the time it takes to complete an orbit also changes, which means the points where the planets meet gradually shift. And at some point, what happens? They coincide with the apse line. The points where the components of the gravitational pull against and along the motion finally balance. And this becomes a stable configuration. The planets end up locked up in that resonance. Similarly, this works if the planet pulls the second one more strongly after the closest approach, just in the opposite direction. In the real world, however, planets still won't stay in such a position forever. As I've already mentioned today, there are other mechanisms that cause moons and planets to migrate. Tidal forces, like with the moon, or the sun losing mass, as in the case of Earth. Moreover, in reality, besides these three bodies, there are other planets as well, which also swing their gravity back and forth. In short, even a stabilized system will eventually become desynchronized. But interestingly, in that case, the mechanism I described earlier can kick in again, and the planets can return to the most stable configuration. And this can continue for a very long time. And if this mechanism is stronger than other influences, the system can remain in resonance for a really long time. This is an example of a stable, self-correcting resonance. It clearly shows what's special about resonances, as opposed to random encounters of planets at random locations. In this example, we saw how one more massive body, when in resonance with another, effectively alters the orbit of the smaller body. In a similar way, Jupiter cleared regions of the asteroid belt and created the Kirkwood gaps. Actually, what we've described so far is a very simplified special case. In practice, resonances are more often unstable. If the person pushing the swing overdoes it, they can send the swinger much farther than intended. Orbits have differing eccentricities, inclinations, and so on. As a result, in about 95% of cases, resonances eventually break down. But every now and then we come across remarkable systems like the TRAPPIST-1, with as many as 7 planets in resonance. Here, scientists actually believe that the resonance may have lasted so long — the system, by the way, is older than our solar system — because for some reason, the planets in that system experienced relatively few collisions with the other large bodies in the early stages. If the period of the so-called late heavy bombardment had been similar to ours, large collisions would have knocked the planets off their orbits, and the resonances would have been destroyed. But we still observe it today. There's still a lot of interesting stuff here. For example, there can be retrograde resonances, where bodies move in opposite directions along their orbits, rather than in the same direction as it is the case in most systems. There's also a special case of a 1-to-1 resonance. Here, since the orbital periods of the two bodies are the same, the planets or moons end up sharing the same orbit. But I talked about such a situation, whether it is possible, in a separate video about the counter-Earth. So check that one out if you haven't seen it. Yes, of course, there are still many nuances, but overall I hope now it's a bit clearer how, besides being a mere coincidence, in certain situations, slowly migrating planets that aren't initially in resonance, once they enter it, can stay in it for a long time. Hopefully this makes it a bit clearer what these planetary nudges are, and the swing analogy becomes a little deeper. There's no magic, no fine-tuning, and no astroengineering by highly advanced aliens. Too bad. Thanks for watching. Links to all of the sources are, as always, down below in the description. And if you enjoyed the video, leave a like, comment, and subscribe for more videos in future. Bye.